We're all used to hard drives for our data, memory sticks for our files. But what if you could build one for light itself? I mean, a device that could literally catch a single photon, hold it, and then release it whenever you want it. It sounds like something straight out of science fiction, but it's a real breakthrough, and we're going to break it all down today.
So that's the big question, right? How in the world do you build a memory stick for a single particle of light? This is one of the biggest challenges in building the next generation of technology, especially the quantum internet. See, to make that a reality, you absolutely need a way to store the quantum information that photons carry. But how do you trap something that, by its very nature, is defined by always being on the move?
All right, so why is trapping light so incredibly important? To understand that, we need to dig into the fundamental challenge that scientists call the quantum memory problem.
So what exactly is a quantum memory? The easiest way to think about it is it's like photonic RAM for a future quantum internet. It's a device that has to do two things, and it has to do them perfectly. First, it has to capture the ridiculously delicate quantum state of a photon. And second, it has to release that exact same photon with all its information perfectly intact whenever you need it.
Now, this is just monumentally difficult for a couple of reasons. First off, quantum information is so fragile. I mean, any stray light, any tiny magnetic field, any noise at all can totally corrupt the photon's state. It's kind of like trying to whisper a secret in the middle of a rock concert. And second, the photon has to be a perfect match for the memory device. Its energy, its timing, its shape, you name it, or the device just won't even see it. For years and years, scientists were making progress, but they kept slamming into this wall, a fundamental limit that was holding the entire field back. It's known as the 50% barrier. In the quantum world, 50% is a magic number. For a quantum memory to be of any use at all, it has to work more than 50% of the time. Why? Well, it's because you can't just copy or amplify a quantum signal. If you lose the photon, its information is gone. Poof, forever. So if your memory device isn't more reliable than a coin flip, you might as well not even use it. And here's the crucial point. For all the attempts, all around the world, no one had ever built a single photon memory that could reliably break this barrier. The best anyone had ever managed was something like 49%. Agonizingly close, but not good enough to be truly useful. Until now, researchers at South China Normal University didn't just inch over the line, they absolutely blew past it. They demonstrated a quantum memory with an incredible efficiency of over 85%. This isn't just an improvement, it's a whole new ballgame. As the researchers themselves put it, this result completely changes the game. It pushes quantum memory from being this interesting thing in a lab much closer to being a practical part for real-world technologies. So, how did they do it? How do you actually build a machine that can catch and release a single particle of light? Let's take a look under the hood.
Okay, this setup looks super complex, but the idea behind it is actually really elegant. It uses two different clouds of supercooled rubidium atoms. The first one acts like a photon factory, creating one single photon whenever they need it. That photon then travels over to the second cloud, which is the memory itself. That's the hard drive for light. The secret sauce here is a quantum trick called electromagnetically induced transparency, or EIT. So normally, that cloud of atoms is completely opaque. But if you shine a special control laser on it, it opens up this tiny window of transparency. The photon goes in, and when you switch the laser off, that window slams shut. The photon is now trapped, and its information gets mapped right onto the atoms themselves. So here's the play-by-play. An incoming photon is split into two separate paths. Both of them enter the atom cloud. Then, zap, the control laser turns off, storing the photon state inside the atoms. After a little delay, the laser turns back on, the photon is released, and the two paths are perfectly recombined, giving you the original particle back, completely restored. You know, one of the cleverest tricks they used was to solve that noise problem. The control laser is way more powerful than this single photon, and any scattered light from it could just blind the detector. Their solution was brilliantly simple. They just angled the laser at a tiny 2.2 degrees. That little tilt was enough to separate the powerful beam from the delicate photon, which slashed the noise. Genius. So, the theory is brilliant, and the machine is built. But did it actually work? The proof is in the pudding, right? Let's look at the data. Okay, check this out. We're looking at the input versus the output.
On the left is the quantum state they sent in, a simple horizontal polarization. On the right is what came out. You see that tall blue bar? That shows it's a near-perfect replica. The information survived the journey. And it works for more complex states too, which is huge. Here, they sent in a left circular polarization state. And again, the output on the right shows that the memory didn't just preserve a simple state, it preserved the really complex quantum relationship within it. I mean, these numbers just tell the whole story. Look at the fidelity. That's the accuracy. It's over 99% for every single state they tested. And then look at the efficiency, the success rate of actually getting the photon back. It's consistently over 85%. These are just stunning results. The big takeaway here is that near-perfect accuracy. A fidelity of over 99% means the quantum information is being preserved almost perfectly. The device isn't just storing the photon, it's faithfully storing its complete quantum state. So we have a working high-efficiency quantum memory. What does this actually mean for the future? Why does this breakthrough matter so much? This matters for three really big reasons. First, it's a critical component for building a future quantum internet, which would allow for unhackable communication. Second, it's a key building block for linking quantum computers together. And finally, it's the first time anyone has just completely smashed that 50% efficiency barrier, and that opens the door to all sorts of real, practical applications. This quote from the paper really drives home the impact. In a quantum network, efficiency gains are exponential. A mere 1% boost in memory efficiency could make the entire network over 10% faster. So an improvement from under 50% to over 85% isn't just big, it's absolutely revolutionary. And so we end right back where we started, but with a totally new perspective. We finally have a truly functional hard drive for a single particle of light. The question is no longer if we can build the quantum future, but what we will choose to build with it first.